Hi, everybody. We'll both introduce ourselves. My name's Adam, Associate Professor at the UBC School of Architecture and Landscape Architecture. We're going to talk about the Evolve building. And to give a bit of context of that building, we'll just start a little bit to talk about UBC. If you didn't know, UBC, we're up in Canada. We're one of the largest universities in Canada by students in terms of kind of a general size. But what's made UBC a bit unique in the last 10 years is that we also have become the second largest university by building stock in North America, and one of few that is self-incorporated as its own municipality and made a decision 10 years ago to use its very large kind of endowed land to develop large residential communities, of which the Westbrook Village community is one of them. This is not student residences, this is really a permanent resident community targeting staff, faculty, as well as residents of Vancouver in primarily affordable mid-rise multifamily housing. And Westbrook is only one of many communities. We're planning to have, I think, a total of 60,000 residents living on campus in these communities in the future. And it provided a really interesting context for this project.
Thanks, Adam. So I'm from ZGF Architects. We're obviously the architect for the project. This is an amazingly exciting project to be involved in. From the outset, working with Adam's team all the way through now with regards to data collection. So ZGF, we're a North American-based architectural firm. I'm based in our Vancouver office in Canada. And the ethos with our design philosophy really centers on higher building performance, and we try and build that into every single project that we work on. Please. Today, Adam and I, we're going to walk through kind of 4 different sections to this. Adam's going to kind of outline how we got to Evolve in terms of the financing and the funding. I'm going to walk through in terms of the design philosophy around the project. And then we're going to start sharing some of the data, which is why you're all here. And we've also got some lessons learned. So we're going to fire through this pretty quickly, and looking forward to the questions.
So we have this Westbrook Village funded by UBC, and rents of those who live there pay for the buildings. And I came to UBC about 7 years ago, and there was a unique opportunity there. A, we have this residential community rapidly being constructed. B, we have a policy landscape, if you're familiar with the West Coast in North America, but particularly in Canada, a very progressive policy landscape with regards to climate action and decarbonization. And we had a federal government funding program to incentivize at least some attempt at doing what was called by the Canadian government net zero energy ready, which is very much analogous in terms of performance requirements of Passive House. And a proposal was struck, and took some years to write it. What if we made one of these 6-story, 111 unit buildings that UBC builds frequently a Passive House certified building, and Passive House Plus even, with PV panels? What if we monitored the building with a type of instrumentation that you'd likely only find in research type buildings, with instrumentation kind of everywhere, almost a full BMS? And what if we also had a sister building, which is what we do have in that community, built roughly by the same developer at the same time, with the same size, but just isn't Passive House, which gives us a very unique opportunity to do site-by-site comparison, where the only differentiator is the performance requirements and nothing else in terms of tenancy, et cetera. And we were successful in winning the grant. And I already mentioned a little bit about the wider context of where this comes. So UBC is very, it prides itself in being quite forward-thinking. It has set kind of very ambitious goals to decarbonize the campus, which I'll speak in a bit. But I mentioned already, this is a university that somehow has, without probably being open about it, loves constructing buildings. And starting in 1996 with the C.K. Choi building, which kind of regionally is recognized as one of the first institutional green buildings of its kind, there's been a legacy. Some of you who might be coming from timber and low embodied carbon construction might recognize the Tallwood building. That was the tallest mass timber building in the world at its time when it was built a few years ago. My office is in the Center for Sustainability, which is a net zero energy building. And Evolve, in fact, was a sort of natural evolution of this to move into what is this sector that UBC is now constructing quite readily, residential construction, particularly multifamily residential construction. And again, and we're going to talk a little bit about lessons learned. The context for this is ultimately, is Passive House the vehicle to decarbonization? UBC has a plan as a campus, as a very large campus, to decarbonize its entire building stock and operations very aggressively in meeting the Paris targets. And a lot of the questions in this initial proposal was, is this the right course in terms of a building performance scheme to get there?
So we're just going to walk through some of the design for the project. So just a refresher, we're talking about Pacific Northwest for the project. It's on Westbrook Village. And in terms of the project itself, it's a 6-story rental residential. It's rental for UBC faculty and staff. This is based on tenure, so 1 year, 2 year tenure, and you know, the staff kind of flow in and out of the building based on their tenure. There's 110 residential units in that, and it's a mix of 3 bed down to 1 bed units. And this is kind of the core to the kind of design for the project. And Adam mentioned this Passive House Plus component. So what we've tried to do is identify what was the core in terms of Passive House principles, but then going beyond Passive House, and that's that plus component. So we've got high-performing windows. This is Initec triple glazed system. We've got a highly efficient mechanical system, semi-centralized HRV on the roof, with post-secondary coil providing both heating and cooling to the airstream. It's highly insulated. We have I think it's a 6-inch or 8-inch of rock wool hung to the exterior. And then the air tightness, we managed to get 0.3 air changes per hour at 50 Pascal. So that's our Passive House. You know, we kind of nailed it. But we also understood that Passive House is part of a toolkit. And so kind of going beyond Passive House, there's one component which we'll touch on a little bit later, but responding to overheating. We did a fair amount of analysis using dynamic modeling with IES, and we found a strategy that used shading and active mechanical. We've also got renewable energy, and this is the Passive House Plus. We have a full PV array on the roof, and that accounts for about 20% of the annual energy load. And then we've also got the monitoring and research, which is really what we're here today for. Does anyone remember the heat dome? It was pretty startling. So we started this project in 2019, and it was a double decision for our client group. And what I mean by a double decision, one was the high-performing component, so going Passive House. The other was helping our client understand that there's a real challenge on the horizon around the warming climate. And it came into reality in 2021, halfway through the design, early construction, and this was the response. So we've got minus 29 there. That minus should not be there. That should be just a straight 29 degrees C. But in terms of the design response, and this was through multiple analysis through the IES modeling, costing analysis, we ended up with a fixed operable shading strategy, plus the mechanical strategy with that post-secondary coil providing tempered cooling to the space.
And now we can talk about monitoring. So, one of the opportunities for this project, and where a considerable amount of the funding and resources have gone to, is metering. Those of you who might be familiar in the commercial building sector, having a BMS in a building is relatively common. Not having lots of meters and sensors in there, but this building is outfitted closer to what you might see when you hear about net zero energy research buildings on a university campus, and they're sensored and metered to the hilt. Well, here is a residential building, somewhat in this gray area between the university and the real world, where we outfitted it. And when I talk about outfitted, each dwelling has a VAV supply air system for the tempered air system. We have flow meters, temperature sensors, sensor points on damper controls, so we know what the thermostats are trying to do. We have the HRVs monitored at each of the points from the wheels to the coils. We have a very full, in fact, and this will become part of the challenge, is a very heavily engineered data infrastructure, which we're now just digging into. And it offers some interesting questions and opportunities around the level of data that passive houses can generate, But then the question is, once a few buildings, and very few buildings, generate this much data and make it transparent, how many stories does it tell about how complex these buildings might actually be to operate? And here's just one anecdote. There's 110 suites in this building, and we could talk a lot about some of the issues that this building kind of encountered in the last year. Here's one of them, August 13. This is one suite where the supplier dampers went to a closed position randomly. By randomly means that there might have been a reason for that. It's smoke alarms, temperatures, ventilation, CO2 rates. There's about 6 levels of control. Yet when we look at what we're getting from the BMS, it's hard to tell what signaled the dampers to close. So what ended up happening is in this one unit, dampers closed. Then clearly in the days following, we had CO2 rates going up. The residents might not have been accustomed to using the windows, or maybe they had the windows open and still CO2 was going up because they were not getting ventilation into areas where this sensor was located. The room air temperature, there was a mild heat wave later in August, and the temperature started going up about 26 degrees. I can do that here. Oh no, I can't do it on the TV, but you see just kind of towards the end of August, the temperatures have some spikes. The residents try to reduce their set point. We can see that. They're trying to hit the button saying, I want it to be cooler, but nothing is working because the damper has stayed closed ever since then. And one has to ask yourself in the residential sector, how many residential buildings have a facilities manager commercially trained to operate a BMS system to find the damper position? How many passive buildings are built with alarm detection of these types of issues? Probably very few. And in fact, what we're seeing with lots of data is just how many more questions it raises about system complexity in these buildings. More to come. In fact, all of this data and this granularity of this data is going to be publicly accessible. We're going to make this building an anonymized dwelling data for sure, but a lot of the mechanical data through to the full building will be publicly available hopefully in the next year, as well as this comparator between Mundell House, which is a sister building that isn't passive house. It's quote unquote code compliant, and we're going to see how the two fare, at least at a holistic kind of building performance scale. Lots more we can talk about data, but probably a teaser of exactly what the data is now starting to tell us.
In terms of lessons learned, so we've started to get these early results through, and I've got some, if you like, findings. One of the biggest challenges we had was the commissioning rolled into occupancy. That's not the ideal scenario. It's typical for pretty much all developers that we work with. They try and cram in the schedule, and commissioning kind of gets left to the end into occupancy. The one real challenge we had with this is the semi-centralized HRVs. They had a factory setting that only allowed 50% of the air coming into the space. That caused a huge issue in the first 9 months, and it took us a long time to find out where that issue was. What we are now kind of looking at is not only bringing in the CA into earlier, but also looking at the core consulting remaining on the project for a little bit longer. So what does that really mean? It means that time and materials response for post-occupancy with the core consulting team helping identify, not necessarily identify, but help problem solve where the issues are. Thanks, Adam. The other kind of early lesson learned we got was we had a lack of the ops team input through the design. So this building ended up being more complex than what is typical for the ops team on site. And on handover, the ops team essentially saw that our windows were opening too far and put restrictors on them. And what that meant was the original design intent of opening the window and being able to access the shading was then taken away. So if we were able to have a discussion with the facility team much earlier, we'd have been able to walk through the design intent, walk through the strategy, help them understand exactly what was being developed for the project.
And I mean, you're hearing this kind of narrative coming through. You know, on one hand, a passive house is clearly more energy efficient, relies on, you know, passive design elements for its general performance. But as you get to these mechanical systems that have a lot more fine tuning, we are, in some cases, increasing complexity, at least in a multifamily building where you have to deal with unit by unit levels of control and the type of mechanical infrastructure that's required behind that. And so, as data is showing, this sort of amount of investment that might be needed for controls, commissioning of controls, and teaching operators about controls might be much larger than we are talking about, really. And it certainly is not a small cost. It might, in fact, be really a trigger point on the viability of some projects at certain scales. And Iain and I can both talk about this. I mean, we haven't talked about this either, but this building came as 2019 before the heat dome. It's also come at an interesting time for discussions that are now increasing very much on the west coast of BC, where we have a zero carbon electricity grid, and I imagine also where all of us are coming from. I noted yesterday, and I mean a few media organizations have been picking this up, that out of all the things that seem to be working well under the Paris Accord is global decarbonization of electricity grids, and that we might in fact find ourselves in 2030 to 2040 with lower carbon grids everywhere. And so if you build a passive house that's electric, or you build a non-passive house that's electric, are we at a point where it's trade-offs between embodied carbon and operating carbon, or are we increasingly finding ourselves in a position where it actually might just be embodied carbon if we're dealing with decarbonized grids in the next 10 to 20 years? And evaluating that in the context of this building is also clearly going to be one of our big objectives, because that changes the scorecard, really, if we are dealing with lower carbon grids all across North America and the world in 10 to 15 years' time. And Iain might want to talk more about how they're dealing with that in practice.
Yes, but I think we'll probably pick that up in the kind of question side of things. But what we're seeing with the balance and is finding that sweet spot with regards to embodied carbon and operational carbon. And we're seeing some early results that's kind of pushing back on driving the operational efficiency. But I also want to underline that the value in terms of the energy performance with passive houses is shock events. It's kind of that long-term resiliency component. So there's many other components that we need to consider when looking at that balance. So there's a lot. This is a nuanced subject that we really need a lot more data around.
That's the right counterpoint. I think that takes us to the end of our presentation.
It does, and I think Adam outlined this. We've got a lot more data that's coming out over the next few years. So this is going to be a continual sharing with industry as we navigate through the data sets.
Thanks very much.
So before Mark and Lois go up, let's beat up the topic of data and how you got data and the decisions you might make differently, Adam. So the first question I have is, when the building came up, was the data readily available? Did you have access to it the way you expected to?
So some might be familiar with so this is not kind of our first rodeo in data collection of buildings. And for commercial buildings, there's a more common protocol. So, what we implemented in terms of a required rule was every data point should be accessible through an API, which is kind of a web-based connection of data, follow haystack naming convention of data points, which is kind of increasingly common within the commercial building sector. So we could have a data handshake and the infrastructure there. That wasn't so much a problem until the contracts were issued and that clause didn't find its way through. And on a previous project in Singapore, we were adamant that the BMS contracts needed to have this clause. You can only find a vendor that knows, even understands what REST API is and haystack is. So here we were in the end training what was a lightweight BMS vendor to kind of understand these protocols, and it took us way longer to do this. But we have experience, so it wasn't like we were pulling our hair out with this. But it's certainly a lot of the sort of lexicon of what the commercial building sector has gotten much further ahead on. For the residential building sector, I think we're not quite there yet, recognizing just how more learning we have to do on this.
So you had a data standard, so you had what you considered to be kind of your approach to data.
There is a data standard. We tried to ask for the data standard. In the end, we had to rename points. We did what, if anybody knows how when you get BMS data, getting it in like the name of that engineer that decided today I'm calling temperature sensor 108.
Their children, their animals' names.
Exactly. And yeah, I had Jeremy in my group. If he's watching, he went through that line by line. We even had, just an anecdote at UBC. UBC hired an engineer who spent years just doing this line by line for BMS point renaming,
right,
just to make BMS points interpretable. And that's a big missing link in the whole sector in this.
So to your point on commissioning and doing more of it earlier, would you commission, maybe have a master systems integrator or somebody who could actually start that process earlier for you on another project?
I have great ideas, but Iain was in the trenches, so you might have a perspective on what you think should be done.
The short answer is yes.
Yeah.
Yeah.
Yeah. We found that involving a master systems integrator early in a big data project is a really good idea, just like you would bring in a certifier or you would bring in, that expertise early.
The one challenge, and Adam's kind of politely navigating through it, the one challenge that really was educating the client and helping them understand the purpose.
Right.
And we were not able to get over that hill. And that's really where we ended up in terms of the data set not being as fully functional as it needed to be.
So one of the things that might be overwhelming for some people is to think of the idea of 5,000 sensors, right? So would you do that again? I mean, with an IES platform and a whole building platform, you don't necessarily have to have 5,000 sensors, but I assume you did that because you had specific interest in the data from those sensors, Adam.
It's a great question. I mean, in the real world, do we need buildings monitored with this level of detail with a human eye and everything? No. But ironically, this building does have, virtually 5,000 control points. Each dwelling, 110 dwellings, each of them having 5 different control signals for a supply air damper and a return air damper. And then, so if you think about the complexity that a passive house multifamily has, there is control complexity there. Whether we admit it or not, we might not be ready to, but it's hundreds, if not more, to thousands of points that might be at play in a passive house multifamily.
So that's the really interesting point, right, is that the beautiful part about passive house is, in terms of design and construction, a dumb building is okay. Like, it can be dumb. But what you're saying is really to optimize on operations and the operating decisions that are made for the life of a building. That's where the data really pays its dividends.
And I'd only add that, I mean, and others can share, it's a challenging market too. What does the mechanical consultant do in this, right? They're not there to advocate. Well, they will, but they're not there to pay the penalty of the operational issue that comes after commissioning. And so is there sometimes an erring towards, I'm offering complexity, but I'm not inheriting the problem downscale? Or am I advocating for simplicity because I know that I'm trying to advocate for simplicity on the operating side? And the fact that there's no investment for this operations, really, and the developers may not even know they need to invest in that. It's a big missing gap at, not the design table, but there's an expert who's missing, as you go into a master kind of operator that's missing at the design table.
I think that really underlines that we need to have the facilities team in much earlier and have that perspective, and we were not able to get that, and that was the big crux with it.
Mark and Lois, did you want to take the microphone and present all of your data? Your 12 multifamily projects you'll be presenting?
Our buildings, I think, are in general simpler, which we can talk about. What happened is Lois and I started doing a presentation and expanded it because we've done now 12 at least passive house buildings where we have at least some data from. And our question is, what could we learn from it? So these are all, the first slide, are buildings, we've done almost all of them with Lois. All of them are fully 100% affordable. And all are passive house except for the 2 Marcus Garvey, because those are our first 2 all-electric buildings, the ground source heat pump. And there was some interesting data we can talk about from that.
And these are projects that we worked on ourselves without Mark. Some of them are in New York, some of them are in Pennsylvania and Connecticut. And we also have a couple of market rate projects in this data set for you to look at, which is nice to see the comparison between market and affordable.
So I think the point on this is there are a lot of different ways to get to the same point. The other thing that's interesting is as the energy code ratcheted up, you'll see that like roof insulation is more. But one of the big issues with these, as someone was saying yesterday, is compared to a single family house, as the volume goes up, it goes up as a cube versus the surface area as a square. So when you get these big buildings, they're much less skin dominated, and you may not need as much insulation.
That's a really good point, Mark. All of our multifamily passive house projects are cooling dominated. It doesn't matter what location they're in. They're just so dense. There's so many people and refrigerators per square foot that the internal gains dominate these projects.
And I think the point here is we have a number of different structural systems, and I'll get to this a little when I talk about embodied carbon. Because we're in New York City It's basically has to be all incombustible, and there's a lot of concrete. But whether it's ICF, block and plank, poured in place, we can meet Passive House, and we can go into details on all of that.
That's right. And to speak to embodied carbon, because we have to be steel, we have to be concrete, we are inherently heavy on embodied carbon. We don't have choice on that, except for maybe we can fine tune the designs a little bit. But basically when we approach a new developer and they're like, oh, do I have to do this? Do I have to do panelized system? And we're like, no, what do you do the best and the fastest and the most economical? And we'll help you detail it properly so that it meets Passive House. That's really the difference. You can do whatever is best for your firm.
So the big point I want to make on HVAC systems is our first few buildings had what we called unitized ERVs. Each unit had its own ERV. And we'll talk more about that later. But our clients quickly realized from an operation perspective, that meant there were 100 filters in apartments that they had to get into every 6 months to a year to clean, and they didn't like that. And people won't let them into the apartments, et cetera, et cetera. So all of our newer ones are centralized ERVs where the units are on the roof and there are 2 or 3 or 4 or however many units, but not many, that the super has to clean every 6 months or a year.
And when we get into the data, I want to just point out that heating, cooling, and all the other loads are mostly electric in these buildings, with the predominant domestic hot water being centralized gas systems, except for the 2 Marcus Garvey ones that Mark mentioned on the previous slide, and we'll show you data on all of those.
So now we get to the fun part.
So a lot of you have probably seen these first 2 slides. I'm not going to go into in too detail. We had a year of data for all of those projects that we've been sharing for over a year. And we only had monthly data at the time. And so parsing out what was heating and what was cooling and what was base load is very difficult. Domestic hot water was simpler because it was almost the only the gas load on the building. So we could get some good domestic hot water data. But and then one of the projects is in Pennsylvania and one of them is in Connecticut, or 2 of them are actually in Connecticut. But those 2 projects that I'm listing here had mini splits as opposed to VRF. So here's the monthly data from that set. And it's like different years of data, right? It wasn't weather normalized, so everybody's looking at the same thing. We just put it up to show predicted versus actual. And this freaks people out, but I'm gonna tell you right now, it's not that scary, because the big difference between the predicted versus actual is just domestic hot water. When you change it to what we actually see in North American use, it actually comes within 10 to 15% of the actual. So the rest of that we think is in common area usage somewhere. What are we not predicting properly in common areas? But again, it's, user occupancy, year, whatever. So most of our Passive House projects are kind of floating in the 30s. This is site EUI you're looking at. And the 2 very low ones, which are, this is a small data set, are our senior housing buildings on this. And we thought that was very, very interesting because they're significantly lower. The first one is the only one that is lower than predicted. And it's in Connecticut, it's in Climate Zone 5, and it's a historic retrofit. It's an Enterfit project. So it just blew our mind. And we went through this data over and over and over again with the owner, and we're like, is this right? And she's like, yeah, it looks right, but I don't believe it. So we compared it to her other projects. And so, this is very, very interesting. And so might kind of lead us to change some assumptions when we're doing senior housing, but we need a bigger data set than this. Okay, so let's move on, because now we're going to talk about. So
I'd just like to add, we've got lots of seats up there if anyone in the back wants to sit down.
Okay, so based on that, we're like, okay, we need better utility analysis. I have 3 slides here. I'm not going to go through these point by point because they're all text. The reason I put it all in here is because I want you to see how onerous it is to try and collect 15-minute utility data from New York. It is absolutely insane. We have spent a year, months and months and months, and hundreds of hours just collecting the data from Con Ed. And so, and then looking through it and seeing this doesn't look right, that doesn't match. We compared it to Energy Star Portfolio Manager. We compared it to WeGoWise, and some of those don't match, and they're all supposed to be the same. So just an unbelievable amount of time just trying to get data, which isn't conducive to really quick decisions on how these buildings are performing. Okay, so go ahead, Mark, you can go next. And we share all these slides so you can see what we went through. So we also got monthly data from the owners, which was good, because when we were looking at Cornell data, which was from a third-party monitoring system, because their SATEC is monitoring the building, it looked very wrong, looked different. It looked like the building was increasing really drastically in energy use, and the owners shared their monthly bills, and it wasn't. So like, really have to be careful before you make any conclusions on the data that you're collecting. Okay, so the methodology for this, so we're collecting 15-minute data. We're weather normalizing. We had for the same year, right? This is 2022 data. We then tried to calculate from that data what was the heating part of that data, right? Because we're all electric, the building's all electric. So what you have to understand about passive house projects, like you probably all do, is they do not respond to outdoor temperature like older buildings. We have older buildings that will respond when it hits 65 degrees and lower, heat starts to kick in. These buildings do not. So we have to figure out what we use for that balance point temperature for heating. We used 55, and the reason we used 55 and below to calculate heating degree days was because that's when they turn their heat over. Cornell Tech, the building owner was like, yeah, they don't need heat. When we get some complaints about when can we turn the heating on, it's usually around when the temperature doesn't go higher than 55 degrees during the day. So then they turn it over from cooling to heating. But if they get complaints from the occupants, and it's only like 1 or 2 usually a season, they'll just tell them, it's an energy efficient building, please just put a sweater on, we're gonna turn the heat on this date, it's really not needed in the building. They've had tenants tell them they've never turned their heat on. So that's one of the things. For cooling, we're still using 65 degrees to calculate cooling degree days. And then what we do is we back out what the base load is once we subtract out these loads, the heating, the cooling, and the domestic hot water. Okay, next slide. So this is what our 15-minute data looks like for each of our buildings. Will you click again, Mark? Because I think one more time. Oh no, I don't know why my titles aren't coming up. Okay, these are our buildings. And I have no scale on the left, I have no numbers, I don't know why I have no data on this slide. It's very pretty. The green are passive house projects with the green on the bottom. The orange are non-passive house projects. The squares are circling buildings for the same developer. All right, so you see I have the developer for the 2 in there. Those are 2 passive house projects, and then the first tall bar is a non-passive house project. The shorter one is the most recent passive house we did. That's all electric heating and gas domestic hot water. The little taller one to the left is gas heat as well. They went back to gas heat for cost. So the right one is just a recently built building that's maybe Enterprise Green Communities, Energy Star. There's a 40% savings between that right bar and the middle bar in energy savings. And if you look at the second 2 that I have in a square, that's a market rate developer. The first building is our passive house building. The second building is a one that was completed in the last few years. That's a 50% savings per square foot of energy over that. Now remember, we're in the Northeast where our electric is very expensive. So the energy savings is 40 to 50%, which is really in line what we thought we were gonna see for large scale passive house projects. The energy savings is in the 20% range, right? Because electricity is still more expensive than gas in the Northeast. So that's really interesting data.
The 2 on the right are the non-passive house.
2 on the right. So what you're seeing at the peaks of these the passive house buildings range from about 32 on the left, which is Cornell, to about 40, which is the first one mark in the box, the first boxed one there, which is Bronx Pro, the MAPES one. And so you're seeing a range of EUIs, site EUIs, from about 32 to 40, most of them in the mid-30s. This is very consistent with what we've been seeing over the last few years. And it's very consistent with their previous year, some of their previous years. Some of them have multiple year performance. A couple of them are increasing a little, like the second bar is a little bit higher than it was when it first started. And we talked to the developer about it, our lovely partner here, L&M, and their maintenance, or the people who are watching the finances and paying the monthly bills said, yes, we understand it's creeping up a little. We're not exactly sure why yet. We haven't delved into it. So the problem is our projects have not traditionally been monitored well at all. We are getting end use data only. We're not getting like, here's your heating system, here's your domestic hot water system, here's your ERV, here's your common area plugs, and here's your apartments, right? At the minimum, that's what we would love to see, but we don't have that breakout. So they have to now delve into their systems and see what's happening. Marcus Garvey, though, which is the same developer, is monitored very well. And so when we go in there, we can actually see what's happening. Those two bars on the very far right is a half a year data for both. So we estimated a full year. We got a good 6 months of like summer to winter data. We got a good span. So we are estimating those far to right. But they're performing very well, even as non-passive house, but their electric is about half, their domestic hot water is about half of what the gas domestic hot water energy uses, right? Because you're talking about a COP of at least 2 for their gas use. So that's what's keeping them in the 30s. Okay, so it's very interesting stuff to watch. I'm really sorry, I had labels on everything. Next slide. So this is an example of a gas meter at Cornell Tech. And what we're trying to do, the red is heating energy use, because that's the ERV. There's some gas heat in the ERV at Cornell. It was one of our first passive house projects. We didn't have the option for VRF for preheating or post-heating the ERV air. So there was a 80% gas furnace in there. So that's our gas, we can see that. And then what you can also see is that the rest is domestic hot water, but that actually goes up in the winter as well, right? So you've got this increase in gas use because of the domestic hot water, because the water coming in is colder. Occupants are colder. They want hotter temperature water. They probably take longer showers. I know me as a passive house consultant, I turn my hot water on and let it get warm in the bathroom, and then I get in, right? Very bad. So this is all you're seeing. This is what my house would look like too. So that also makes it difficult for us to take out base load. What's actually base load? What's actually heating energy when we only have 1 meter? Okay, next one. All right, so we have, as a firm, we've done audits on hundreds of buildings, existing buildings. And this is data that my existing buildings teams just shared with me in the last month. I think we've been asking for data for a long time. And they were like, oh no, we have 300 buildings. I was like, okay, thank you. So this is domestic hot water use. What you see in the first 5 bars are market rate. Oh, Mark, will you click again? I think I put a bar on. Those are market rate multifamily buildings in New York. The next go back. The next 5 are affordable. You can see the shift up. What each box is showing is a certain type of domestic hot water system, right? Like it's a gas boiler, an oil boiler, a steam boiler, or something like that, right? So that's what each one of those recommends. But look at the shift up for affordable. So then if you click again, I've added the data on the right from our new data sets that we're talking about today that I just showed you before. We're in line with market rate. Those are our market rate in the box, and then affordable jumps up as well. So we've been contesting that affordable uses more energy because it's more densely populated than market rate. So I think this is really good data to support that energy use, right? Okay, next step. And this is just all of that data in a table format. And what I'm showing here is, if you look at in the original comp set, which is the first 4 lines, the difference between the market rate, average EUI per square foot for domestic hot water, and the affordable median EUI is 54%. If you choose the median of that data set, if you choose the mean, it's 50%. So they're using 50% more domestic hot water in affordable housing. When we add in our new buildings, our 10 new buildings, it's very similar, 53% to 49%. So the strides in domestic hot water use have not really, in the supply system, the heating element, even though those are much better, we're still dominated by circulation losses and end user cooking, cleaning, all of that.
So why is this? And I think there are 2 or 3 reasons. First of all, affordable units tend to be smaller, but we also think they're uninvited guests. If your brother is going to be evicted, are you going to let him go to a homeless shelter, or are you going to let him sleep on your sofa? If he sleeps on the sofa, he's going to use hot water, he's going to cook, he may have a computer, et cetera, et cetera, et cetera. And so there is a big difference, we think, in the density of people and the use. Also, with affordable, people are less likely to go out to a restaurant and spend more time in their apartment. So there are all these factors that we think are explaining why the affordable use. And Lois was talking about hot water. I think you see some of the same things in plug loads for the same reason.
Agreed. So now that we have this data and we've been struggling with it and rustling it to the ground, what's our next step? So phase 3 of our utility analysis is going to be looking more closely at that balance point for heating, for the heating demand. Where are we actually seeing the heating energy come onto the building? So we're gonna evaluate different base loads under which we think heating is. So we started with 55, we're gonna go to 50, 45, and 40. We think somewhere in there, and it'll depend on the building and the surface area to, volume ratio and things like that. But that will help us better correlate the data to the heating degree days and cooling degree days. So we're looking at these, R squared numbers on how well does our curve, our actual data fit our curve, our predictive curve, and they're not great right now. So we need to do more evaluation on these balance points for heating and cooling. We think there's a wide swath of temperature where you don't need either. We think it's probably more like 45, 50 for the heating side, up to 65, 70 for cooling. So we're going to come back with that in our next iteration. The reason all of these projects were in New York, I should mention, is because New York City Accelerator we are a contractor to them, and we're helping them evaluate what does this mean for the grid, what does this mean for our local law 97 requirements, because above a certain carbon use, you're gonna have to start to pay fines eventually. So what we've successfully shown is that passive house projects continually are performing below those fine levels. And it's just it's a great assurance to our clients too. Like, I show this data to our clients when we do kickoffs. I'm like, you are gonna be fine if you go for this. Even if you don't actually achieve it, if you actually go through all the QA, QC steps that you need, you will be fine. Your building performance will be fine. Even if you don't get that final certificate, you have to go for that certificate. That's the important thing. We also are studying, under the DOE's help, 3 buildings really in depth. So more like what you guys did for the university, a lot more sensors. We're measuring indoor relative humidity in at least 10% of the apartments in 3 very large multifamily buildings in New York. We're measuring, and 2 of them are passive house, 1 is not. So we've got ERVs in 2 and exhaust only in the 3rd. And we're looking at indoor relative humidity, temperature, ERV operation, supply stream temperature and relative humidities from the from the ERV. We're just monitoring the apartment loads for all of this stuff. We're hoping to come back to you with, how is our ERV strategy working? Are we in dangerous levels for this, for winter or summer? Is it actually pulling out particulates still? And are we measuring indoor air quality at all? No, okay. But CO2? No, okay. There's only so much the DOE will pay for. So, but we were lucky to get this. So we're a good several months. We got good summer data. And so now that we're going into the fall and the winter, it's really going to be telling, how well. The other thing I don't think the non-passive house building with the exhaust only had flow measurements in the apartments, did it? At the exhaust only systems? Do you know if it was Energy Star or something like that, where they would have tested? Some testing. Okay, good. That'll at least give us some indication. So next time you see us, we should have some really interesting data to share with you on this. They're measuring the VRF systems. They're measuring everything. So it should be a really interesting set of data. Okay, Mark. And this is the other thing we're looking at. We're looking at peak heating demand versus outdoor temperature. And the light blue colors are existing buildings that we have heating demand data on, 15-minute data, and are very responsive. It's almost linear, the response to outdoor temperature. So as the temperature drops, heating goes up. The low 3 are passive house projects. And so what they're showing is the buildings don't really demand at all to temperature. Now, here's the 3 in the middle there are actually 3 passive house projects. And we were like, something doesn't look right, something doesn't look right. This is why data analysis is really kind of tricky. So Friday last week before the conference, I was like, can we get on a call? This doesn't look right. So we started to look at the data in different ways. What is this total up to? What is it not? And it looks like somebody converted to kBTUs, but it was really kilowatt hours or vice versa. And so this is like 3 times what it should be showing in those 3 graphs. So when we correct that data, and I find that those are going to squash down with the other 3 passive house projects. So the important part of these slides are to show policymakers and people that are going to require passive house that this is not going to put in undue pressure for new buildings on their electric grid systems. Okay, so if we want to electrify all of our heating on new buildings, this should not cause problems. Existing buildings, different story. And this is the data that we're going to look at. We're also going to look at the data compared to building stats. Like, what's driving the heating and cooling demands? And is it percent Well, what percent is the heating and cooling of the total site EUI? So you can see all the site EUIs here that you couldn't see on that other graph. The orange, again, are the non-passive house projects. And then what's interesting to me, and I put them in order of lowest to highest site EUI. What's interesting to me is it seems like at the end, what you see is the surface area to gross square foot ratio, that ratio of the building. Cornell's the lowest at 0.53. And as we go up, our site EUI goes up, and basically our heating demand goes up. Now, please don't give too much credence to these heating and cooling pullouts. This site EUI is definitely a good number. Trust that number. The heating and cooling, like I said, I don't think we're using the right balance point to pull out the heating and cooling for those buildings. So we're going to delve into those buildings a little bit more. But I think there's not really a strong correlation yet between some of these other characteristics that I put up and what the site EUIs are. We did a bunch of super interviews, and these are older ones. And some of the input that they gave us was they need a technical report from the HVAC vendors. They didn't get additional training at turnover, right? So they go back to the vendors all the time if they have a problem. They don't really know how to handle it on their own. The setup is important. Troubleshooting has been an issue for them. If one condensing unit is down, a whole line of apartments that goes down. So things like that. One of the buildings set the limits in the apartments at 72 in the winter and 68 in the summer, so that they couldn't go higher or lower than these. And like Mark was saying earlier, sometimes they want them 80, and sometimes, he's got a good slide on that. Right. And then cooling is needed beyond the traditional turnover date for cooling. You don't use more cooling in a passive house project. I just want to make that clear. Your peaks are lower, but you need it for longer. So overall, it's not going to add up to more cooling than a traditional building, but you can't just shut it off October 1st. It was 84 degrees October 2nd in New York. If they turn these over, they're going to get everyone complaining, right? So you have to know your building. You have to know how it responds to the outdoor temperature. And then ventilation is, I don't even know what to say about ventilation anymore. It's like my number one nightmare. Central, individual, no, this doesn't work the way it's supposed to. We can balance it. We can get them tight. We can get the flows right.
So in Beach Green Dune 1, we actually got some decent resident survey data. And we learned some things also tied with the super. People were complaining about smells. And we said, that's weird. We've got ERVs. They should be getting fresh air. People found that there was a circuit breaker in their panel in their apartment that if they turned, these were unitized, if they turned it off, it shut down the ERV, and they said, doesn't make much difference, saves us money, maybe $1 or $2 a month, but I understand. But the side effect of that is they're not getting ventilation, and their smells and their neighbors' smells are starting to be there. The other thing we found is people want it in the 80s in the winter and then the 60s in the summer. And we really need to do education plan. If you're cold, don't turn up the heat, put on a sweater. And if you're warm in the summer, put on a short sleeve shirt. Don't turn up the heat. But there is a real issue that particularly Americans are used to not controlling their environment by what they wear, but by what the temperature is in the room. And now I want to talk, we are getting close to being done of doing an early design award of excellence from NYSERDA on embodied carbon in a project like most of the ones we've shown. And it is eye-opening because 70% of the embodied carbon is in concrete blocks, concrete plank. And we've been looking, our next step in this is saying, okay, are there ways we can reduce the embodied carbon without too much cost? But for example, on concrete plank, you can get in the South a carbon cure concrete plank, but none of the New York City manufacturers are doing that. So till the technology share is expanded, the other thing is it's very hard to get data from manufacturers. But what is clear is concrete, steel, glass or metals, glass and insulation are 95% of the embodied carbon. And so although we worry about other things like carpet or whatever it is, that isn't the big issue. And just many of these have come along, but just sort of quickly, clearly you can do passive house a lot of ways, and we had more. Operation and maintenance is really key. And the area that we can make gains on is hot water. Either the Beach Green, the Marcus Garvey have ground source heat pump hot water. We're also looking at wastewater heat pump hot water. We are doing some air source heat pump hot water, which is not as efficient. And also because it's using a lot of electricity will cost significantly, about 20% more than a gas-fired boiler at current rates. And we can go in onto other things, but I think this covers it.
Yeah, you know, and I want to echo what Iain and Adam said about having the O&M staff in the design phase. We did a tour of Cornell a few weeks ago for Columbia, who's looking to do another dorm. And the maintenance and operations people were with us there too. They had so many interesting insights into how the students actually use their apartments. They're not technically dorms, right? They're small apartments because it's grad housing. And like he said, simplest stuff. Give them a shoe rack in the closet, because everybody goes out and buys a shoe rack for the semester and then throws it away at the end of the year. And so what they started doing was they used the bike room as this whole staging center where they collect all the stuff and let the incoming students buy it, right? So like the insight, he's like, you don't need a 4-burner oven for the students. Give them a 2-burner. That's all they need. The grad students are not cooking Thanksgiving, you know? It was really, I was kind of blown away by how much he knew how the building, besides energy, performed sustainably. So like, absolutely bring him in sooner, absolutely.
I'm an outlier. I did cook Thanksgiving as a grad student. I would also add, the other thing of real interest is, for these affordable housing buildings, for 100 units, we'll get 100,000 applicants. People want a new, safe, clean apartment. They're not looking like the original single-family house for a bespoke passive house because they're really green and want to lower their carbon footprint. Some of them say, yeah, that's nice, but they're not going to think about their behavior in reducing their energy consumption.
Okay.
So as we transition to taking questions from the audience, and I'll head out there with the microphone here, just let's beat up your mechanical systems a little bit. So based on everything that you've learned, if you had your dream system, what would it look like and why? How would you design it?
Okay, I would, especially speaking from an embodied carbon standpoint, sorry if Mitsubishi is in the room, I would not go with VRF. If we wanted to use heat pumps and do central heating, I would go with a hydronic system where the heat pump that's either geothermal air source that feeds the rest of the building. This reduces the chance for leaks, for harm to the occupants, and it's just a much more elegant solution. I would also, on the other hand, all of these high performance individual cold climate PTACs, you know, the little heat pumps that go through the wall, those afford an unbelievable cost savings to the owners. It's in the millions of dollars, depending on the size of the building. So to be able to, and they get individual control when they want it. There's no changing the heating and cooling over in the building. They want cooling, they hit cooling. If they want heating, they hit heating. So there's pros and cons of that from the developer's perspective if they're paying for those utilities. But from a control and a comfort standpoint, I think that's great. And if you go with the original system that I was talking about, the hydronic, you can also very easily loop in your domestic hot water, because you can use the hydronic loop to feed some of your domestic need and put a water-to-water heat pump in the building to do that. So that's what I would advocate for. I would get away from these huge central refrigerant systems that run refrigerant all through the building.
Hi, Bronwyn Barry here, Passive House Network. Very interested to hear your embodied carbon kind of overlays as you're bringing that into the analysis of your projects. And the comment about, you know, how are we looking at the balance of operational versus embodied as the grid decarbonizes. And I want to just do a shameless plug for the PHN pH ribbon tool, because it's a plug-in to PHPP, and it actually has that slider that you can draw down the grid's, the impact of the grid in that tool. It's a really amazing way to look at it. But the question I have to you then is, are you now looking at the passive house elements as a resiliency response? And what's your sort of reading the tea leaves as you look at that and bring that embodied carbon factoring into the equation?
I think it was really interesting seeing the slide that you brought up showing the concrete component. Concrete far outweighs an awful lot of the materials, but at ZGF we're carrying out a huge amount of work to reduce the carbon impact. Volume reduction, so much better strategies in terms of understanding what the foundation plans are, all the way through to reducing transfer slabs, and then walking through mixed designs and making them performance-based, not prescriptive. So there are some really easy things that we can do for all projects, not just passive house. But then, with regards to higher building performance, I think there's a real nuance in there in terms of what the impact is between embodied carbon and operational carbon. Where some of our colleagues in and around Vancouver are saying that we should be at step code 2, step code 3, and then be looking at embodied carbon. But I want to see the results that are coming through from those individuals. Are they using XPS insulation rather than higher performing insulation? So this is kind of the start of the question. I'm really intrigued to see where it kind of goes.
I first want to answer the resiliency and then the embodied carbon. We had a slide that we took out because of time, but all of what Lois was showing, the temperature doesn't change quickly. So if you've got a building in the winter, it's not going to get cold very quickly, and just all the people in there are going to keep it warm even if you had no heating and cooling. And to some degree, the same thing in the summer, particularly if people open windows at night and close them at the day, et cetera. As to the embodied carbon, and I understand, my guess is that it's more about the materials, because our buildings aren't that far above what code requires for the envelope that we're really putting in lots of extra stuff that may save a little energy but increases the embodied carbon. And again, concrete and steel. The other thing I've learned, which is really interesting, is both most of the steel in the US and Canada and concrete is dependent on your electric source. So in the Pacific Northwest or in Ontario, where there's a lot of hydroelectric, their materials are lower embodied carbon because they're using the electricity that's clean.
So thank you all. This is fantastic data. You're total heroes, especially Evolve, for all of this data you put on the table. And full disclosure, I was involved with Evolve, so I have some details here. You made a decision to cool via ventilation air. And you kept saying in this presentation, oh, the passive house is so complicated, it's so complicated. But I just want to note, you made a decision to cool via ventilation air, which made it very complicated. And you're doing the monitoring, so it's a great learning experience. And it's interesting that the first example you have, and I know this is going to go on for years and we'll learn a lot more, is that you had a failure exactly where we feared there might be a failure, that if those duct dampers failed some way, you could overheat. And you were showing 27 degrees-ish without a heat wave, just a hot week. If we had another heat wave like 2021, and we will, it looks like you could have the potential to overwhelm that system. So the question is, and I do want to hear from everyone on this, this was a great experiment. Would you again combine ventilation and cooling air, or would you prefer to separate them through one of the two types of systems Lois had talked about?
Short answer is separate. But I think it's really good to understand why we got to that system. The constraints that were placed on us through the decision-making process. It was the first time that cooling was being considered by or I should say, first time that overheating was being considered by the client group, and trying to walk the line of meeting the cost component where there was not the desire to put that on the pro forma. So it was a long, hard discussion, and you were definitely there, Monty, for that. But yeah, I mean, if we're doing it again, it would be separated.
And I remember being there advocating the system that you were advocating, and it would be too expensive, but I really don't see how it could have been. You know, if one at the end of the day, this is probably still a quite expensive system that was implemented.
Don't feel bad, because we're certifiers on a project in Vancouver that tried to do this as well, and it's not doing a good job. Separate them. It's way too complicated.
Hi, I just wanted to know whether changing filters every 6 months, is that working out? Or, I mean, in terms of how clogged the filters are when you change them, just on a very practical level, I just am curious about.
All right, I'll share some dirty laundry. One of those projects on there, the Passive House one, that has individual ERVs. And we have been commissioning that building for 3 years because the HVAC contractor said he balanced them, nothing was touched. Everything was in the original settings on the ERV when we went in. So our team has, and it was during COVID too, and it's occupied. So we're trying to get into these apartments to balance them. There's only 30 apartments. We're almost done. It's been 2 years. So every time we go in, the first thing we do is take the filters out, because we learned that if we're going to measure flows and the filters are clogged, we're not going to get the flows. So we take the filters out. There was so much dust on one of these filters that it fell back into the duct and was just a lump laying there. On top of the filter was like this. And this was the third time we've talked to the super. You have to clean these filters. And they were like, we are, you know, the developer's like, no, it's in the protocol. They told me they changed them. I'm like, this has not been changed in a year. Like, there's no way. Or since the day it went in, it's got to be 2 years that it hadn't been changed. And so that was an issue. And then the last time we were there, that causes more problems on the exhaust side. Typically what we see is okay. Then last time we were there, we were getting no supply flows in 2 units, and we're like, something's wrong, because they used to have supply flows in these. We've never been low on supply. And we go outside, and sure enough, the intakes are completely caked. Completely. Like, you had to use a wire brush to get it off. And they don't have a window wash drop system. So we're like, okay, how are you going to clean this? And we brought this up during design. We're like, you have to be within hand reach so that your maintenance people can get out there and vacuum these off. You can't reach them. The wall is so fat, and you can't see what you're doing. You need a mirror on it, you know? So what they wound up doing was retrofitting the ERV inside with a little, almost looked like a drain, you know, like a cap thing there, where they put a access into their ductwork, and they're using a leaf blower to blow the dust off from the inside, and it goes shooting out. We have pictures of this happening. So this is, we swear, don't do individual. We just swear, like, just don't do it.
I would add, in general, unless there's a problem, we don't hear from clients. So I wish we could do more post-occupancy surveys. Clients are understandably concerned about asking too many questions, but we don't hear unless something's leaking or really not working, because they deal with it however they deal with it and don't tell us.
On the grid decarbonization question, I think it's a really important one for us, I think, as a community to grapple with. And one of the things that I'm learning is that just as buildings are these integrated systems, the grid is as well. And so I'm from Seattle, and the Seattle City Light is a publicly owned utility that calls itself the nation's greenest utility, because we get our electricity from hydro. But the reality is that Seattle is integrated into this larger grid. The grid is meant to be connecting all these different utilities together into a big system. So the EPA guidance in terms of how to understand what my electricity is in terms of the carbon intensity is to look at the subregion, the eGrid subregion level. So ours is the Northwest Power Pool, and that includes like Washington, Oregon, Idaho, Nevada, and Utah. So while we are putting in, my utility is putting in clean electricity into that large pool, the electricity I'm drawing out of it is the average of all of that electricity. So it's roughly equivalent to the carbon intensity of burning natural gas for heat. So that's where we are now. The exciting thing is that we're going to be decarbonizing, and there's a great tool to understand the implications over time in terms of the carbon intensity of grids, at least south of the border. And that's NREL's Cambium tool. And it projects what's going to happen in the next couple of decades, and therefore what makes sense in terms of that operational carbon, embodied carbon balance.
You know, if I can only speak to that, you know, separate to this, we're doing an analysis just on that same point, looking at these large kind of regional scale decarbonization. And, you know, as you get to a carbon intensity of using natural gas for electricity, the life cycle carbon over 30, 40 years is actually not as much as when we were using coal for grids. So that's the point that we're already kind of at a point where things are lower and only getting kind of lower. And that in the end becomes a question like boundary conditions that are interesting to me. Largely when we're going to talk about the building stock and electricity grid and resiliency of the electricity grids, it's the existing buildings that are our problem. New buildings are generally in most places a drop in the bucket in terms of affecting grid, maybe over some scale, but really in the future we're dealing primarily with the buildings we have today. And when we want to talk about how 20% of global carbon emissions from the building sector and where that comes from, 40% globally and 20% out of that 40 or 50% of that 40 is construction of just the few new buildings we do. So ultimately, I can't see how we're not going to only be talking or primarily be talking about embodied and the fact that we're in the Wild West. How do you do a 30-story wood building? You know, we're totally 30 years away from knowing how to really fix this problem at a scale, but I think we're maybe we've not moved fast enough, but we're now starting to move much faster to realizing this, I think.
Thanks, great talk. I think it's really interesting to note, by the way, that you're creating buildings that need almost no heat. And I think it's kind of a basic point that we take for granted, but I wonder if the general public and the developers actually fully understand that, because that is such a massive, massive point. So question, on my projects, which are obviously much smaller than the ones you're dealing with, I cannot get clients nor contractors to want to monitor their buildings for different reasons. The contractors, which I'm assuming is much more difficult on your end, are definitely afraid of litigation or other issues if it's not performing the way it is. So I'm assuming there can be some legal language that protects them, wondering if you've got that in place, because I think monitoring is so important. And then the last one, which is the all-in-one system. I would like you to temper my enthusiasm over some of the new ERVs and so forth that are coming out that do provide some cooling and so forth. You said you wouldn't do an all-in-one system. I would like to do an all-in-one system. So wanted to get your sense on some of the products that we know are soon to come on the market.
That's a good point. Thank you. There are individual systems that are high performance heat pumps that go in the apartment. They're like vertical PTACs, but they also provide the ventilation. And I think they're working with PHI to get those certified. So we don't have any experience with them yet, Mark, but the fact is our cooling loads require higher flow rates than our ventilation does. So you would still need to increase that flow. And so we'll have to see how it comes out. But I would be more comfortable if it was definitely a certified product to put it in a project. And I think one of our certification projects is considering that right now. So, yeah.
The monitoring question?
I would just say we're actually using those units in 3 projects that are high performing but not passive house. So yeah, it's kind of it does make sense, and the bit that we like with it is the controllability for the user. That's the instant heat, instant cool, depending on their needs. So that's the.
And it's exactly that same reason where I have anxiety on it, as we're noticing that at the user end, they become a bit more complex in terms of education of the user and control, because they're trying to do a lot of things with a VAV box, CO2, heating, cooling, all together, smoke alarms and dampers all working together. It's a commercial building BMS operation point to a resident that would have no idea that there's that much complexity in that control point. So I think as a system, it works really well, but that complexity has a cost implication to it.
And to talk to the fear of like data, I've run across that too, but most of our affordable housing developers keep their buildings. They want to know what's going wrong. It's in their best interest to know how they're performing and to keep their utility bills down. And so it's not like it's being shared, you know, like the residents know if their bills are high, right? And they're going to ask why. So, but I think most of our affordable developers who hold their buildings and are doing passive house want to perfect this. And anytime I can share data on a previous project of theirs to help the mechanical engineer understand, no, that's too many geo wells, you know, you're not going to have a peak heating load that high. That's always well received. So there's more benefits to monitoring for these buildings. Market rate, I'm not so sure if they have the same feeling.
Thank you so much for your awesome presentations. I'd love to hear some more elaboration about two things. One is space cooling. What are some non-mechanical strategies for space cooling, external shading, solar heating coefficients that you think are worthwhile? When are they worthwhile? Where do you see that going? And then similarly, for domestic hot water, where do you see that going? So just love more elaboration based on your experience on those two things.
The Evolve shading strategy was hugely complex. It took a lot of work with the CM and a CM that was really engaged. So the contractor was engaged really, really early on in the project to help us with understanding what was capable with fabrication locally. Alongside that was very in-depth IES modeling to understand what made the most sense in terms of depth of shading, you know, east, west, south. You know, what was the combination of active shading, so operable by the users, and then fixed shading. It was a long process, but that in combination with the temporary cooling was the design intent for that final solution.
Shading, yeah. So our buildings are 2-to-1 internal gains to solar gain. So teaching the tenants how to reduce their load from internal is really important. If you're not using the light, turn it off. Turn off your TV. If you're not using it, turn off your appliance if you're not using them. It's really just coming from inside. Yes, solar shades absolutely can help you, but there's a lot of issues with them if they're not designed right, and they can be complex. I would not recommend movable ones, especially in high wind areas like off the coast of Austin. In our high rises in New York, I would not, recommend adjustable ones. I would recommend fixed ones that are designed well to take the majority of the solar load away in the winter. I mean, excuse me, in the swing seasons in particular in the summer. We have such high humidity. I don't know that natural cooling really helps much unless it's the swing seasons. It's not like Colorado. Like you can open a window here, it goes down to 40 at night. It might be 90 during the day. It goes down to 40 at night. You flush your whole house out. It's beautiful. That doesn't happen in Connecticut. I mean, you need the fans on you from every direction if you don't have cooling. And I know that because I haven't had cooling until this year. So it's just so humid that it's hard to do natural cooling.
I talk about shading. Most of our buildings are block on plank, and the walls are 18 to 20 inches thick. And so inherently we get shading in the design. Now, as an architect, we've done our 4697 3rd Avenue has these really nice shades, and we have some really nice pictures, and they look great, and they do shade a bit more, so it's not a bad thing from that perspective. But just thinking it animates a facade if you do it right, so there may be other advantages besides lowering the load. On the hot water question, what interests me are ground source heat pump, wastewater heat pump, other things where you can extract. Also, is there a way in the summer, our hot water system and our heating and cooling system are typically separate, But in the summer, where I'm creating lots of heat by cooling the apartments, can I capture that heat for hot water instead of throwing it out? So I think hot water is actually where there are the most opportunities to save more and to be continued.
And I'm just going to add, I noticed a data point that you had. I wonder if history will judge it this way, but I think, passive house as a standard doesn't play nicely with double loaded corridors in buildings. If you cannot get ventilation, then you're going to have a shoulder season where you have cooling in October where you could night flush, but it's because when you open the windows, you get no fresh air. And I think typologically, it's difficult. It's an urban design question. It's a planning decision whether you could have single loaded corridors, which means you're able to ventilate through a unit from one end to the other. But fundamentally, it's probably where the Europeans have had an advantage with their typologies and where passive house seems to be working in the shoulder seasons a little bit better than it is for ours in these shoulder periods.
I would argue it's both a cost, they're less efficient plans, and also often a zoning question.
I don't disagree with, but that goes to the question of where passive house plays with that.
So I'm going to make a plea to everybody who's involved in planning next year's Passive House Network Conference that we do more of this, because as we start to get data, you all have so much rich experience and we're learning so quickly. A little bit to the point Bronwyn made in the 8 o'clock session, we have to be patient and really figure the data out and not be quick to, or knee-jerk reaction our way to, okay, well, let's do this then, right? To your point, Adam, the data's complex. So I'm getting the wrap sign 1,000 different ways here that I have to wrap. Like you can't even imagine. There's neon signs everywhere. But I do want you each to have, 15, 20, 30 seconds to give your final thoughts to the audience.
I think that people who are saying, why should I do this because there's minimal savings, are wrong. There's significant savings. And we're now getting the data to show them. So we're going to quelch that pretty soon.
I would say we have a balance of data and the fact that this is the existential issue of our times and we need to move quickly. And I'm not sure exactly what the right answer is, but we keep needing data.
Forward is good, is what you're saying.
What?
Take a step forward. Forward is good.
Doing this is
Doing
good,
something,
even
yes.
if we don't quite know what the best way to do it is.
Yeah, I think of something clever. We just did a project out of hempcrete. If somebody can figure out how to do a 20-story hempcrete building and get away from concrete, they'll be a billionaire in this carbon world we're dealing with.
I won't end in something smart. In terms of these passive house projects, the one thing that we kind of really took away from it was understanding the end user, like who's the occupant, how they're going to use the space. And that really ties back to controllability. How are they going to control their space? And ultimately, it leads to simplifying the mechanical system as much as possible.
That's great. So if you were an absolutely fantastic audience. The questions were so high quality. So thank you very much. If you would join me in thanking our panelists for a really great session. Thank you.